Brandon Wisnicki from Suncoast High. So also Brandon has an amazing, interesting background. What really struck my attention is that in his spare time, like I don't know what you were doing when you were 16, but Brandon in his spare time is programming and he builds video games, and actually if you go to the Apple Store, you can find one of his video games, 5-star reviews. And actually what he did in this internship is apply his ability to do video games to basically do a video game for mice, right?
Yeah. Thank you. Can y'all hear me okay? Okay, perfect. Hello, I'm Brendan Wisnicki. I attend Suncoast Community High School in the computer science program. For the past 6 weeks, I worked on building virtual reality for mice in order to study the hippocampus in the brain. This is my drive from my house to Max Planck. The first few days, I needed to follow my GPS or I'd be completely lost. By the end of the first week, I didn't need my GPS as much, and I just kind of got there on my own. By the end of the 6 weeks, driving this route became almost muscle memory for me. And knowing the different visual cues, such as intersections and stop signs, told me when to turn right or when to turn left or when to switch lanes. So in the past 6 weeks, I created a memory for myself. But what is a memory? Of course, it is what we remember in the past, but how are memories created? How can a bunch of neurons in our head create the detailed memories that we remember? This is the question the Wong Lab is asking. The Wong Lab is currently seeking to understand how the circuits in our brain generate patterns that allow us to remember to think, plan, and remember. Basically, how do we remember? This is the human hippocampus. The hippocampus is in charge of memory. Named from the Greek word seahorse due to its curved shape, the hippocampus plays a vital role in memory creation. Now, this is the diagram of the hippocampus in a mouse. Studying the brain, specifically the hippocampus in mice, is key to understanding the human brain because of our genetic similarities with these rodents. So how are we able to actually study these mice and their hippocampi? A T-maze is a simple T-shaped corridor that gives a mouse a choice between two different directions. T-mazes are the classical way of studying mice and the memory of brains. These experiments have been used since the beginning of the 20th century. The subject is often given a kind of stimulus that shows how to go into a certain direction. For example, it could be given a positive one, such as cheese, or it could be given a negative one, such as Tom. T-mazes are used to study memory. For example, if there is a reward on the left side of the corridor, the more trials the mouse does, the more likely it will go to that left side. Repetitive tasks like these create memories in mice that allow us to analyze the hippocampus effectively. This is just like how driving to work every day creates a memory on how to get there for us. These mice learn where to go in the maze. So this is what a typical physical T-maze looks like. The mouse is placed in a small compartment here, and the stimulus is placed on either side. When the trial begins, the walls are lifted to allow free movement of the mouse. These physical T-mazes present many difficulties in doing memory-related experiments. Physical mazes are very inflexible because there must be room dedicated for an actual physical maze, and creating more complex mazes can take up more time, resources, and space. Mice, just like humans, have a lot of senses. These mice have types of senses that can be affected by stimuli, such as whisker or tactile cues. The whiskers of a mouse are full of nerves that allow it to sense many different, difficult-to-control factors, such as air pressure. We want to be able to control as many of these sensory factories as possible, and physical mazes make that very difficult. So virtual reality can alleviate a lot of these issues. My project for the past 6 weeks was to create a small form factor virtual reality system that allows the mouse to actually be in the VR. This is a basic example of a virtual reality system. As you can see, the mouse is here with a small head fix to keep the mouse's head stationary. There's a treadmill that the mouse will run on to actually allow it to move through the maze, and then there's a large screen surrounding it with the actual virtual reality display. With virtual reality, we are able to easily control and isolate the different senses of the mouse in order to make our findings as accurate as possible. For example, there's only one type of air pressure, no smell cues and stuff that could confuse the mouse. It's only visual. The VR system that we created has many physical components that communicate with the VR software that I've built. This is the treadmill. When the mouse runs on this, the system records its speed, and information is sent to the VR in real time. These are the two lick ports. The mouse licks the two metal rods when making decisions in the virtual reality. These two metal rods can deliver water droplets right through here when a mouse is given a reward. Finally, the last main component of this system is the head fix. This keeps the mouse's head stationary in order to allow us to actually study the mouse's brain. With all these components, we need a way to display the virtual reality simulation to the mouse. This is a curved screen that allows the mouse to actually see the entire projection. The virtual reality is projected via a projector right here, and it displays it and displays the image through mirrors to display it right to the mouse. This fully immerses it into the virtualized environment. For the past 6 weeks, my project was to program and create the 3D virtual reality software. This means building the course the mouse will go through, along with the communication between the different physical components and software. In this example, like I said earlier, this is the curved screen that the mouse will be fully immersed in. This is the treadmill that the mouse will run on. These are the two lick ports that the mouse will lick to make decisions or to actually get water droplets delivered. And finally, this is the head fix that will keep the mouse's head in position. I use multiple programming languages such as MATLAB, C# and C++ to develop the whole system. Currently, the mouse runs through the virtual reality corridor and sees visual cues such as circles, rectangles, or X's. In this example, as you can see here, there's an X-shaped cube over and over on the right side of the wall. One of the basic trials currently is the mouse should lick the same rod that's on the cues. So in this example, since the cues are on the right side, the mouse should lick the right rod and it'll get a reward. There are more complex examples, types of trials as well that we're trying right now, such as multiple cues on both sides. If the mouse correctly chooses, it gets a reward of sugar water automatically. While the mouse is going through the trial, equipment is measuring the brain activity in the mouse's hippocampal region, helping us pinpoint the neuronal mechanisms of memory creation. The system is fully automatic, water is delivered to the mouse automatically, and the trials are restarted by the computer as well. One second. It's frozen. Oh, there we go. All right, here we go. So this is the VR in action. One second. So as you can see here, the mouse is running through the virtual reality system. When it stops on the treadmill, the virtual reality also stops. As it speeds up, the actual objects in the VR move faster as well. This is just like, let's say you're driving down the highway. You can see objects, when you move faster, they move by you quicker, and when you stop, obviously, everything around you stops moving. So this is a basic example. The mouse can run about 150 trials for about an hour and a half before it gets tired and demotivated. Every trial, we give it a small water droplet to motivate it to actually keep doing the trials. Currently, the virtual reality stimulates the mouse, and we record the mouse's response in the brain activity. So right now, there's a visual cue on the screen, and the mouse's eye senses that and responds to the brain activity. In the future goal, our future goal is to design a closed-loop system in which the virtual reality reacts back to the brain activity of the mouse. This will allow us to study the brain activity of the mouse even further and understand the hippocampal region as well. I would just like to say a huge thank you to Dr. Yingshui Wang and the rest of the Wang Lab for helping me in supporting my project. I would like to thank Ilaria for supporting me and my fellow interns through the entire internship experience. I would like to thank my fellow interns for having a lot of fun throughout the 6 weeks. And finally, I would like to thank both the Max Planck Institute and the general support of the Brain Trust members. This opportunity is phenomenal for me, and I'm extremely grateful for it. Thank you.
Questions for Brandon?
Could you rephrase that question? And using like humans? I'm sorry, I'm confused.
Well, is there any possible way to study the memory using, like scientific books or, some kind of like knowledge without actually, using the actual specimens like people or mice?
So the question is regarding if we can actually do trials and study the hippocampus of a mouse without actually having the mouse physically there or actually using any animals. I'm mainly a programmer, so we can talk about that with my mentor, during lunch. Thank you.
But the short answer for now, no.
The question is regarding how much I actually had to code to make the system work. So between the 3 languages I used, I think the whole system uses about 1,500 to 1,700 lines of code. The virtual reality system that actually displays it uses about 700 lines of code to actually show the display. Right, that's a great question. So the question was regarding how we actually use our equipment to study the hippocampal region in the mouse. So here's let me get to it. So here's the example. In this example, you can see there's a probe directly in the brain. Right. In certain cases, and as long as we keep it different, so yeah, we can have a probe into the brain to actually study the memory. The question is regarding the actual rewards we use to motivate the mouse. So right now we mainly use sugar water, but we use sucrose water, right? And we also use regular water. Sucrose water has a much stronger motivation because the mouse likes it more. So we use both to reward the mouse. The question is regarding my future, my career plans. I really love programming. I definitely want to do something in computer science, and this internship really opened my eyes because, when you finish school, I thought you're done learning, you just work. But this is the kind of career that you just keep on learning, and I absolutely love that. So this has definitely changed the way changed what I want to do, but I still want to keep it in the computer science field. Thank you.